Hello friends, continuing with pharmacodynamics, today I'll be discussing about the dose response curve. And as the name suggests, it is a curve which uh, equates, or you can say which relates the dose to the response. Okay, so for making this dose response curve, what we do is, say you take an example of a person or an isolated tissue, and what you do is you keep on giving incremental doses. You start with some dose and then you keep on increasing the dose, and you also observe the response. So giving all these doses and finding the response, what you do is you plot it on the graph paper. So if I have this graph paper and something like this, I have an, so there is, this is the x-axis, this is the y-axis. On the x-axis we plot the dose, okay, and on the y-axis we plot the response. Okay, so what we have seen is whenever you increase the dose, what you will see is the initial doses may not give you any response to begin with. Then what happens, at some dose a response starts. Okay, say for example, for giving this much of dose nothing happens, then you see that a response occurs. And what you see with giving again next doses, you will see that the response, it follows a pattern something like this. So what you are seeing here is it will start off, so very small increments in doses will lead to an increased response. See, for example, this much of a difference of a dose, here it is giving you so much of a change in the response. And in the beginning you will see something like that, and towards the end what you will see, the increments in doses will not lead to much of a difference in the responses. Okay, towards the end you will see that this response curve, it is now flattening. Okay, so this type of this graph which you have got, or the curve which you have achieved here, it is called as a hyperbola. Now this hyperbola curve, this you will find, because this is just equating the dose with the response. So as you increase the dose, this you can visualize in an experimental setup. So there is nothing to this is a normal what you will find out whenever you are going with the doses and responses. But this type of a curve is not very beneficial for making out many conclusions. It is not a very beneficial curve. So what we do, and another thing is, whenever you are using this type of a curve, this type of dose response curve, you will need a very large graph paper for plotting. For reaching this maximal point, maybe you will need 1,000 of doses, and that may not be possible on a single small graph paper which you have. So what we do is, instead of this normal dose response curve, the practice is to use another type of a dose response curve which we call as the log dose response curve. So log means we take the logarithm of the dose. So what happens there, if I take the log of the dose, it gives you one benefit. Again I am plotting it like this. This x-axis is, here I am taking the log of the dose, okay, and here again the response is there. So now what does logarithm do? Logarithm converts a geometric progression into an arithmetic progression. Means the doubling of the dose, if you keep on doubling the dose, which is normally a geometric progression, it converts it into a arithmetic progression, and you can plot the every double dose, it can be plotted on the graph paper as an equal interval. Okay, so if I'm doubling the dose, it is adding 0.3, then another doubling of the dose will add another 0.3. So we can simply plot this logarithm on a very on a small constructed piece of paper. We can very easily plot it. And you know, as you are increasing the dose in doubles, you can reach a very large amount in very few intervals. So generally the practice is, for obtaining this dose response curve, the practice is you keep on doubling the dose and then you apply logarithm. When you apply logarithm, what happens? It becomes arithmetic and it is easy to plot it. That is one thing. And another thing, another benefit which it provides you is, it gives you some sensible type of a curve, and that curve is, it looks like somewhat this, something what we call as a sigmoid curve. It is a sigmoid curve, and this sigmoid curve, it has some benefit over the hyperbola, which I have already discussed. The one benefit that it provides is, it can be accommodated on a single graph paper. One very important thing. Another thing is, now you will require very less number of doses to reach this in the maximal response. So as you are, if in this case of log, if I am giving the doses, like say it is 1, then I am doubling it 2, then doubling 4, 8, 16, 32. So you know, you can see that I have reached 128 in just 7 or 8 readings. Okay, if I was going by the other one, I would have given 1, 2, 3, 4, 5, 6. So I would have required a very long graph paper for plotting. Here I reach these values, 128, 256, 512, in a very short interval. So this gives me a benefit of plotting it at a faster, you can say at a faster rate, and giving you a very beneficial curve. The benefit of this curve is, as you can observe, nearly from this point till this point, the curve is a straight line. And a straight line, you know, a straight line is always beneficial, because you can extrapolate this straight line, and this can give you some meaningful results. Like you can identify what is the effective dose, or ED50, or you can say the median dose that can be calculated. So many benefits are provided by the straight line. So this log dose response curve becomes much better an option than the conventional dose response curve. So this is one benefit which we get from the log dose response curve. Now this type of dose response curve which we have discussed is on a single subject. This type of dose response curve is also called as a graded dose response curve. Graded because you are increasing the dose and you are seeing the response in a single individual. So this is a different type of setup. Another type of setup is what we call as a quantile dose response curve, and there what we do is, we take a bunch of individuals, or say a fixed number of experimental animals, and then we give the dose to all those individuals and see the response in all of them. And the thing is, there what we do to the response, we make the response as fixed. We fix a response. Say for example, if we are going for a toxicity study, and what we do is, in case of experimental animals, we are looking for the toxicity of a particular drug. So what we do is, we give some dose to the all the experimental animals, and we see on giving that dose how many of them die. Okay, so then what we do, say for example, out of 50, say we take 50 mice, and we give some dose, say 2 milligram, and 2 milligram kills 2 mice. So what we'll do is, we will in this case what we will do is, this is the dose, okay, and here the on the y-axis what we plot is the frequency. Frequency as in how many. So if 2 milligram leads to death of 2 mice, so this is my first point. Okay, then say I increase the dose to 4 milligram and then I see another 5 die. So now it will be somewhere here, 5. So it goes something like this. Then maybe I give another dose, so it keeps on increasing somewhat like this. And what we see is it keeps on increasing, going up to a maximum point, and then it keeps on decreasing. So it gives you a curve which is bell shaped. Okay, and this type of a curve is normally what we call as a normal frequency distribution. So this is a normal frequency distribution curve which we normally see in many other conditions also. So here you will see that there is a maximal frequency which will be shown at a dose which is somewhere in the midpoint of the minimum and the maximum, and towards the this end you will see a very small frequency is exhibited at here and a very small frequency will be exhibited at here. So this is one case where I am discussing lethality or death of the experimental animal. It can also be like a response, say for example a fixed response, like I say a maybe anesthesia for example. So anesthetize, you're talking about general anesthetics, and you see how many people are anesthetized by this much of a dose. So what you will see that there is a small frequency, small population which will respond at very small doses. Okay, and you will see that there is some population which will respond at a very high dose. Okay, and maximum you can say that say 95% of the population will be seen which fall to this, which we call as, you can call this as a sensitive, means 95% of the people they are sensitive to this dose ranging from here to here. And then there are some who are hypersensitive since they have responded to a very small dose, and then there are some who are hyposensitive. Okay, and these are some which we call as the hyposensitive. They will fall towards the extreme this side, extreme right side of the curve. You will have some people who respond less and there are some who respond more, and then maximum of the population will be lying between these two limits. So this can also be found out by applying those two standard deviations to the mean. So that is a different story that will be discussed elsewhere. Anyways, so this is an important type of dose response curve, what we call as quantal. But again, this dose response curve is not very beneficial. It becomes more beneficial when we go for a cumulative dose response curve. The cumulative is here I was not adding the previous number to this frequency. So an increased dose, say for example it killed 5 more mice, I used only 5. I did not add 2 to the next number. So if I add that amount to the earlier number, what will happen is you will have a response curve something like this, where the frequency is now cumulative. So I will write here a cumulative frequency. So cumulative frequency would be like, so if there are 2 here, so this is 1, then add this to the earlier one, so maybe it is somewhere over here, then here. So what happens is ultimately it reaches 100%. So all of the animals, they have died at this dose. And what you will see is this again is somewhat like a sigmoid curve. It again, when you join the midpoints, it somewhat looks like a sigmoid curve. I will create it again here like this, somewhat like this. It is a simple sigmoid curve, and then you can calculate things like what we call as a mean effective dose or effective dose, which will seen in a 50% of population. This is called as ED 50. So effective dose in 50% of the population, or if we are talking about toxicity, so it could be lethal dose. Depending upon what effect we are seeing, if we are looking for effect or efficacy, so 50% efficacy will be seen at this dose. It means that 50% of the population will have a, a benefit or that effect which we are looking for. And if we are talking about toxicity, so 50% of the animals, they will die by this dose. Okay, so this becomes an important thing, and why I am stressing on this ED50 or LD50, these two are actually responsible for what we call as another concept called as a therapeutic index. So there is a term called as therapeutic index. This is actually a ratio of the lethal dose LD50 divided by the ED50, means the dose which is lethal in 50% of the individuals divided by the dose which is effective in 50% of the individuals. The ratio of these two, or the division of these two, would be called as the therapeutic index. Now you can see, if the lethal dose is more and effective dose is less, what will happen? You will have a higher therapeutic index. Since the ED50 is in the denominator, if the ED is less and the LD is more, the therapeutic index goes higher. And the higher this therapeutic index, the safer is the drug. Means the effective dose comes in even in a lower dose you get the effect, but the lethality is at a much higher dose. So increased therapeutic index, or you can say a higher therapeutic index, means a higher therapeutic index means safer drug. It's a simple thing. Just on the basis of this, because the lethal dose is much higher, effective dose is much lower, so the drug becomes safer in this case. Okay. This is one important thing which we get out of the dose response curve. I hope I am clear as of now. Then there is one more thing which we need to know from this. There are two terms. One is what we call as potency, and another what we call as efficacy. Okay. Now, potency is a function of the dose. We can say a dose which causes a particular response. Okay, so means if there are two drugs and one drug, it causes some effect at a dose of say 5 milligram, and another causes the same effect at a dose of 10 milligram. So the one which is causing an effect at a lower amount or a lower dose would be called as more potent. Okay, so in case of, if we are looking at a dose response curve and there are two drugs, the one which is having, say I am plotting dose response curve of two drugs like this. This is how you see the dose. One drug is showing an effect at a lower dose here, and another one is showing a response as a higher dose. So the one which is showing a response at a lower dose would be called as, say for example, this is a drug A, this is drug B. So I can say drug A is more potent than B because it is towards the left on this curve. Okay, so this is one important thing. Another is the efficacy, and efficacy means the maximal effect which you can see, means it is independent of the dose. You give any dose, and means what is the maximum effect. After some point, the maximum response, you cannot go beyond that maximum response. So say for example, in these two drugs, if you will see, the maximal response of drug A and drug B is same. So efficacy wise, drug A is same as efficacious as drug B. Okay, because the maximal response is same. So efficacy is the maximal response which can be produced by the drug irrespective of the dose. Okay, and potency is it is related to the dose actually, because the drug which provides you a particular response on a lower dose would be called as more potent. It is the drug, and potency and efficacy, they are unrelated in a way. A drug which is more potent may not be as efficacious. So you will find drugs, they give a response at a very small dose, but maybe not as efficacious as another drug. So these are two different things, and there are functions of different. So potency is more of a function of the affinity. The more potent drug will bind very fast, so it will respond, and the more efficacious drug or efficacy is a function of the intrinsic activity of the drug. Okay, so that is about today's lecture on the dose response curve, potency, efficacy, and therapeutic index. Thank you so much.